Okay, for this lesson, we're going to talk about reflection and refraction. And a lot of this has come from the base knowledge that we have in grade 8. We're just going to build on it. The law of reflection is where we have the angle of incidence equals the angle of reflection. And the really key piece here is about the line of normal. So the angle of incidence equals the angle of reflection about the line of normal. And this is the normal line, this dotted line here, that's 90 degrees to our surface area. And one of the things that we know, we've studied so far, is that energy travels in two paths. It travels in waves, and it travels as particles. And when we talk about energy, we're going to specifically talk about the light energy. This energy, this wave theory and the particle theory supports the law of reflection. If this is a wavelength of light coming in, or whether this is a photon packet of energy coming in, they both reflect about the line of normal equally. So the dual particle wave particle model of theory is supported by this law of reflection. Refraction is when we're looking at moving between two mediums. I should be clear, two different mediums. Okay, and it changes direction. So what we're seeing is that if it's passing from, say, air, which has an index of refraction of 1, into water, which has an index of refraction of 1.33, if this is the line of normal, it's going to come this way and then bend. Okay, and we'll talk about this line of normal changing closer to the normal or away from the normal. But we can mathematically figure out this law of refraction. We can figure out the relationship of how the electromagnetic radiation bends by using what we call Snell's law. And so Snell's law in our notes is all four of these. Sine, and this is key, it's the sine of the angle 1 over the sine of the angle 2 can be equal to, pay attention, the index of refraction, N2 is over N1, wavelength 1 over wavelength 2, or wavelength 1 over wavelength 2. I'm highlighting this N2 over N1 because the index of refraction, if you look, it's 1 over 2, 1 over 2, 1 over 2, except for the index of refraction is 2 over 1. Okay, so theta is the angle measured from the normal, so this angle here. N is the index of refraction for a specific medium, and either you're going to calculate it or it's going to be given to you. Wavelength of light in meters. This isn't written in stone. As long as both wavelengths are in the same unit. Okay, then it's okay to leave it as nanometers or picometers or micrometers or however it is that we're measuring it. 1 and 2 subscripts indicate different mediums. And this one here, you're only ever going to be looking at two variables. So you could be looking at sine is equal to N2 over N1. You could look at lambda 1 over lambda 2 is going to be equal to V1 over V2. You could have V1 over V2 is equal to sine 1 over sine 2. Okay, there's lots of different variations. It's just one group will be related to another group. Okay, the key takeaway here is that there's no frequency. There isn't an F1 over an F2. EMR, as it goes from one medium into another, the frequency doesn't change. So if it's leaving the air at 30 cycles per second, otherwise known as a hertz, it's going to go through the glass at 30 hertz. Okay, the speed changes, but the frequency doesn't change. The wavelength to time ratio stays the same. Index of refraction is how we look at optical density. Optical density just being how are we perceiving what we're seeing. Okay, so it's a measurement of how easily light can travel through a medium. If you have a low index of refraction, so air is 1.00, it's pretty easy for that to travel through, the EMR to travel through it. And so what we see is it speeds up as it gets lower. So here, if we went this way, n is equal to 1.00 and n is equal to 2.42. These ones here will travel faster, and as you get closer this way, they'll travel slower in the mediums. A high index of refraction, like a diamond, is difficult for light to travel through, and that's where diamonds get their brilliance from, because once the light enters the diamond, it bounces inside of it. There's tons of reflection going on, but there's very little refraction going on. And the more that it bounces and carries that light, the more it sparkles. Index of refraction has no units because it's all based back to a vacuum. And what do we notice about a vacuum to air? Again, they have the same values. So if we were to look at this question, a beam of red light has a wavelength of 700 and is traveling through water, which has an index of refraction of 1. So red light has a wavelength of 700 nanometers and an index of refraction of 1.33. The beam leaves the water and travels into a piece of flint glass, and so it has an index of refraction, that's wavelength, index of refraction of 1.75. First part of the question is, what is the wavelength? So when we go back to Snell's law, when we go back to this relationship here, and we're looking at wavelength, and we're looking at index of refraction, we can compare those because that's two variables. So it's wavelength 1 over wavelength 2 is equal to n2 over n1. Remembering that this n relationship is reverse to everything else. Okay, so n1 then, wavelength 2, would be equal to n1 times lambda 1 divided by n2. So 1.33 times by 700 nanometers divided by 1.75, and lambda 2 is going to be equal to 532 nanometers. And we go back to our first lesson where we're shown the spectrum, and we have written down the Roy G. Biv, and this is at 700 nanometers, and this is at 400 nanometers. We see that 500 is right around the green wavelength. So this beam of light, what's happening is there's a wavelength coming in at some angle, but 700 nanometers. And it's going to go from 1 to 1.33. So that's going to slow us down. So we're going to get this smaller angle. It's coming in at red and it's coming out at green. Okay, just the same idea as a principle working through this. This is water. This is water. And this is glass. Okay, and then it asks us compare the frequency of the incident wave to the refracted wave. So then what we can say here is that because frequency never changes between mediums, your frequency 1 would be equal to your frequency 2. Okay, that it doesn't matter if it's water into a diamond or air into plexiglass, the frequency never changes. A student is doing a lab and measures the speed of light to be 2.21 times 10 to the 8 as it travels through a certain substance. Use the table below to determine the identity of the substance. So we're going to look at this question, and it says, as it travels through, so it's coming in, here's our line of normal. Always, angles are always about the line of normal. It's coming in at 2.21 times 10 to the 8, and it's asking us to determine the identity. And in order to determine the identity, we do that through the index of refraction. So this is what we're looking for, is the index of refraction. Now, it's traveling through a certain substance. Well, it doesn't tell us what it is, so let's pick air. Because air we know is 1.1 and 3.0 times 10 to the 8 meters per second. Okay, those are givens. We know those pieces. You can find both of these values on your constants in your data sheet. So we see this because it's going it's speeding up. If it's going to get faster, it's going to move away from the line of normal. So this angle is going to get bigger. So as it increases speed, it moves away from the line of normal. And so we can look at this relationship. Remember that N2 is over N1, and we can put it in relationship to velocity. And we're looking for the index of refraction. We're going to set it up like that. You can also cross multiply, but this is what cross multiplying looks like when you write it out. So here's my N2, my V2, and my V1 goes in the denominator, and I end up with a refractive index of 1.357. We can see here that all of these go to 2 decimal. So if we round this up, we get 1.36, which is going to tell us that the other medium is ethanol. So our unknown substance equals ethanol. So we're going to take a pause here, and we're going to go work on these questions here. These ones are easy peasy basic. 204 is asking you just to do the first row, and then 209 does 17 and 18 for intermediate. Let's look at this though. Before you do that, let's look at this page 19 in the workbook. And it looks like this. This is on, I can't remember what page, 210 probably. It's saying here, Aidan sets out to determine the speed of light in a viscous fluid by using the principles of refraction. When we have the incidence angles, we only do the math with this, the sine 1 over sine 2. So we need to take these angles, and we need to calculate out the sines of these angles. So I'm going to quickly run through that with you. I'm going to cheat. Okay, so if you did the sine of each one of those, you should have come up with these values. It says determine the sine of the angles and place it in the data. Place the data in the chart. Plot the sine of the angles. We're going to plot the sine of incidence on the x, and we're going to plot the sine of refracted angle on the y. Then through your calculator, you're going to determine the slope. And in order to do that, I'm going to borrow Brendan's calculator. In order to do that, we're going to go stat, and we're going to go edit. And you can see that there's data in these points for Brendan. They're actually the data that's already here. I'm just going to show you. If we go back to stat and we go 4 for clear list, and then we're going to pick second L1, that's the list 1, and then we're going to go stat 4 to clear the list, and then second L2 to clear that list. When we go back under stat and we go edit, we can see that these cells are empty. So now we're going to go and we're going to go over to list 2. We're going to put those numbers in. Okay, so we've got all of our data entered in. It looks like it's right. I apologize if there's an error. Okay, now what we can do is we can go back to stat. We're going to go over to calculation, so calc. And we're going to go down to number 4, which is linear regression. And we're going to say, yes, x is my L1, y is my L2. And I'm going to go down to calculate. And it tells me that the formula for the slope is y equals ax plus b. We're used to seeing m in this position, but a or m is still slope. And it's asking us here, determine the slope of the line. So when I look at my regression, I can see that it's approximately 0.8464. Now, this is an angle, the sine of an angle divided by the sine of an angle, and so there's no units at this point. And then it says in line D, use the slope to determine the speed of light in viscous fluid. Once we know those pieces, we can go sine theta 1 over sine theta 2, and speed we know is v1 over v2. We can look at, we're looking for v1, we know is going to be the speed of light. Sine theta 1 is x. Sine theta 2 is y. So what was the point of calculating out the 0.8464? Well, when we're looking for v2, and we rearrange this formula so that we follow y equals mx plus b, we can say that sine theta 2 is going to be equal to v1 over v2 times by sine theta 1 plus b. Because sine theta 1 is x, sine theta 2 is y. What's the relationship between the two? And it's the relationship that this piece is, v1 over v2. V1 over V2 then translates into the slope. So I can say the slope is equal to V1 over V2. It's asking us to solve for V2. V2 is going to be equal to V1 over slope. So V2 would be equal to, and when we go back through the calculator, we can say 3.8464. We get 3.54. Did I do? I got this part wrong. Hang on, Harveys. I got this wrong. That's okay. We're allowed to make mistakes. When I rearrange for sine theta 2, this flips. So sine theta 2 is going to be equal to sine theta 1 times V2 divided by V1. That was the error that I made. I didn't do this step. I just jumped and I made a mistake. So this is actually V2 over V1. So then this changes. It's okay to make a mistake. So V2 is going to be equal to slope times V1. So V2 is going to be equal to 8.464. It's also my reasoning for don't write in pen. Equals, let's try this again, 0.8464 times 3, whoops, to the power of 8. There we go. That's much better. We can't go faster than the speed of light. That would be time warping. Okay, so V2, 2.54 times 10 to the 8 meters per second. And that's how I know I had done something wrong, because I got 3.54, and I was like, wait a minute, that's higher than 3.0. So I knew that I made a mistake. Okay, my mistake was that I didn't go back to the basics. I just solved for sine theta 2. I just tried to jump straight into this, and I made a mistake. Okay. The next thing that we're going to look at is the critical angle. So sometimes what happens is light will come in as it's traveling from one medium into another, and it ends up just hanging. And it doesn't come back, it doesn't reflect back into the medium, and it doesn't come out into the next medium. We call this the critical angle. So it's the refracted wave to be 90 degrees to the normal line. So here's our line of normal. And we can see that this critical angle here was met. Okay, and so it's always equal to 90. The angle of incident angle and the refractive. The critical angle is always the incident angle and the refractive angle is always 90 degrees. Because it doesn't come out, it just stays there. Okay? In order for it to travel along the boundary, the wavelength must be traveling from a high index. So, something higher than what you're looking at to a lower index. So typically you're traveling from some medium like glass or water. I know water is 1.33. diamond equals 2.42, and we're traveling into air. So it's that coming out angle. So what happens is when we are greater than that critical angle, then we get total internal reflection, and so it stays in this point. It would just stay below in this medium going up and down. This is actually really important. Where would we see this happen? We see it happen in fiber optics. This is how fiber optics cables can travel. So like the SuperNet is on a fiber optic cable from Grand Prairie to Fairview, and the strength of the signal isn't lost because it never goes outside of the glass fiber that the wavelength is traveling in. It just stays inside, being reflected inside of it. Total internal reflection. Okay? It gets trapped within the first medium. Okay? It can only occur when it goes from a high medium to a low index of refraction. So this one says calculate the critical angle for the diamond air boundary. So we can call this diamond, and we can call this air. And so this here, right, always about the normal. This is angle I. It has to travel from high to low. If you're wondering why I'm picking diamond to go first and then air, right here, it has to go from high to low, both for internal reflection and critical angle, high to low index. So this has got an N of 2.42, and this has an N of 1.00. This becomes N1, this becomes N2. The other part that's really important is that the refracted angle will always be equal to 90. So 90 degrees, and it's asking us for this angle. The angle of incidence will always be the critical angle, and the refracted angle will always be 90 degrees. So remember this, needs to go from high to low. Has to go from a high index of refraction to a low index of refraction. Your angle of incidence is your critical angle, and your angle of refraction is 90 degrees. Those always have to be that way. So because we're looking at angles, we can look at sine theta 1 over sine theta 2 is equal to N2 over N1, remembering that this is always opposite. Our critical angle is sine theta 1 is going to be equal to N2 times sine theta 2 all over N1. So sine of theta 1 is going to be equal to N2, which is 1.00, times the sine of 90 divided by 2.42. So the sine of the incident angle is going to be equal to 1 times the sine of 90 in the brackets divided by 2.42. So this is the sine of the angle, 0.4132, which means that theta must be equal to second answer, 24 degrees. This is the critical angle. This is if it's going to not come out, if it's just going to hover along the line, it's going to be 24.4 degrees. This is 24.4 degrees because this is the angle of refraction. Okay? Let's look at this. Use the diagram to answer the next question. Find the minimum index of refraction the prism needs in order for the light to follow the path as indicated in the diagram. This part here, this inside, 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 this is what we're calling total internal reflection. Total internal reflection. Okay, and in order for that to happen, the index of refraction has to be greater than the critical angle. Or the condition that the critical angle puts us in. Okay? So, when we come in about the line of normal, it comes in, here's 90 degrees, 45 degrees, it hits this side of the prism. Draw the line of normal 90 degrees to the surface. So if this is coming in at 45 degrees, then this angle here is going to be 45 degrees. 90 minus 45 right here equals 45 degrees. It's going to come and hit here, and then it's going to come back out. Medium number 2, well, medium number 1 is the prism. Medium number 2 is air. Okay? So, N1 is what we're looking for. Find the minimum index of refraction. Remember, this is the critical angle. And the refracted is the 90 degrees. So this medium here has to be N1. N2, 1.00. Angle 1 is going to be 45 degrees. It's coming in right here at 45 degrees. Angle of refraction is 90 degrees because we have this total internal refraction. It doesn't come through here and come out. It bounces around inside the prism. Okay? So when I set it up, sine theta 1 over sine theta 2 is equal to N2 over N1, and this is what we're looking for. So N1 is going to be equal to sine theta 1. Or I could use, this is 1 and this is 2. I call them I's and R's. So N2, 1.00 times by the sine of 90 degrees divided by the sine of 45 degrees. Put that in the calculator. We're going to make sure we use brackets. Brackets, brackets, brackets. 1 times the sine of 90. Enter, divided by bracket the sine of 45. 1.41. So N1 equals 1.41. Does that check out for total internal reflection? What did we say? The index of refraction has to be greater than the critical angle condition. Well, the critical angle condition is 1.0. Is 1.41 greater? Yes, then we've done something correct. Whether we've gotten the answer right or wrong, we've done something correct. Okay, so this is the minimum angle. The minimum, the minimum index of refraction. If we got a number that was any higher than this, like 1.42, and yes, it's that close, any index greater will cause internal, let's put the word total here, total internal reflection. Okay, so key points that you have to remember. The index of refraction has to be greater than the index of the incident, and the critical angle is the incident angle, and the refracted angle is 90 degrees. Those have to happen. Otherwise, you're not going to get critical angle, and you're not going to get total internal reflection. So this is the end of the lesson. You're going to work on these questions, 20 through 27, try 25, and try number 7. Challenge yourself, push yourself.